Hi everybody, hope you're having a wonderful day. Today we're going to finish our notes on stoichiometry and we're going to start with dilutions. So when you dilute a solution, if you have a concentrated solution, to make it more dilute, you add water to the concentrated solution. And so your initial flask has a concentrated solution, you're adding water to it, and so you're not changing the amount of solute, you're just changing the amount of solvent or water. And so your moles of solute before dilution are the same as your moles of solute after dilution. And so we use the equation M1V1 equals M2V2. The reason why that works is because M1 is basically moles per liter, so it's moles of 1 over liters 1. V1 is your volume, so liters 1. And then molarity 2 would be moles per liter for your second solution. V2 would be the volume in liters of your second solution. So if you look at this, your liters 1 cancel, your liters 2 cancel, and so moles 1 is equal to moles 2, which is basically what we had said, and so that equation works. So let's look at a problem. It says, what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.10 molar sulfuric acid solution? So we have a very concentrated solution of sulfuric acid. It's 16 molar. We want to make a dilute solution that's only a 10th molar. And we want 1.5 liters of that 10th molar solution. And so basically it's asking how much of the concentrated solution should we use. So you're going to set up your equation. As soon as you realize that it's dilution, you're going to use M1V1 equals M2V2. It's a pretty easy equation, it's plug and chug, but a lot of people get these wrong because they don't put in the numbers in the correct spot. You have to realize that these two numbers are for the same solution, so these go together as one of the solutions. And then this one is by itself as your other solution. So let's plug that in. So M1 is going to be 10th molar. V1 is 1.5 liters, M2 is 16 molar, and V2 is the volume of the 16 molar that we are trying to find. If you plug it into your calculator, you get V2 is equal to 0.0094 liters. So what that means is 0.0094 liters, that's 9.4 milliliters basically. And so what that means is you're going to take 9.4 milliliters of the very concentrated solution, you're going to put it in your flask, and then you're going to keep adding water until you reach 1.5 liters. Your ending result will be a solution that is a 10th molar. The next topic we're going to talk about is titrations. And so titrations are basically a lab technique. So it is a lab technique. It's used a lot with acids and bases. That's when we used it last year, but it could be used for other reactions that change colors, for example, or that you can use an indicator for. And so the idea is you have a burette. If you remember, a burette kind of looks like a really, really, really long, thin graduated cylinder. These are graduations here. But then it has a stopper at the end that you can turn on. If it's parallel, that means it's on. So your solution that's in your burette will go down. If it's perpendicular, that means it's closed. If it's parallel, that means it's open. Then you have an Erlenmeyer flask at the bottom. And so last year, we put acid in an Erlenmeyer flask, and we added an indicator to it that would change colors when the reaction is done. And then in the burette, we typically add the base. This year, we are going to do acid-base titrations, but for this specific lab that we're going to start tomorrow, we are actually doing a redox reaction. Remember, different transition metals, when they have different oxidation states, they turn different colors. Like manganese, for example, when it's +7, it's purple. When it's +2, it's colorless. And so we're going to use that to kind of tell us when to stop our reaction. So we're not actually adding an indicator. But usually, if you're doing an acid-base reaction, you add an indicator, and that tells you when to stop your reaction. So the idea is, let's go with the acid-base example here. So your acid is in your Erlenmeyer flask. Let's say your indicator is phenolphthalein, for example. And so you want to titrate the acid with the base. And the point of titration is to determine the concentration of an unknown substance. So either you don't know the concentration of the base or you don't know the concentration of the acid. You only know one of the concentrations, and you use Stoich calculations to figure out the concentration of the other one. The substance that you know the concentration of is called the titrant. It's what you titrate with. The substance that you're trying to analyze is called the analyte. And so you add both together. So in this case, we are adding the base to the acid in the flask until you see a color change. So in this case, we said it was phenolphthalein. So when it turns pink, for example, that tells us that they're neutralized. And so we stop our reaction. So the end point and the equivalence point should be kind of similar, but they're not exactly the same thing. The equivalence point is where your titrant has completely reacted with the analyte based on the stoichiometric ratios. So if you've used up both of the reactants, so you don't have any limiting reactant or any excess reactant left over. That's your equivalence point. That's really where you want to stop your reaction. In order to tell when the equivalence point happens, typically you use an indicator that turns colors. And so the indicator, when it changes colors, that's where the end point is. It's when the indicator changes color. So we usually pick an indicator that will change color at where the equivalence point is about to happen. And so usually these are pretty close to each other, but they're not exactly the same. And when we get to acids and bases, we'll talk a little bit more about that a little bit more in depth. So again, you add the analyte to the titrant up to a certain amount when your color changes, and you will know how much of your titrant you added, how much of your analyte you added. You know the concentration of one of them, and so you can use stoichiometry to calculate the concentration of the other one. So let's try an example. So here's our first titration example. It asks how many grams of zinc metal are needed to react exactly with 50 milliliters of a 0.25 molar solution of hydrochloric acid. Actually, this is not really titration, but it is solution stoichiometry, and you do the titrations exactly the same way. So since it's talking about a chemical reaction, the first thing that you want to do is write out your chemical equation. So we have zinc, so Zn, reacting with hydrochloric acid, so HCl. You guys are all expert chemists. You know the products. This is single replacement. The zinc will come in, kick out the hydrogen, so you're going to form H2, and then zinc chloride, so ZnCl2. And just so you can all sleep at night, we need a 2 here so that we can balance it. The second step, I like to just write my numbers underneath my substances here. And so we're trying to find grams of zinc, so I'm going to put question mark grams. We are given that we have 50 milliliters of a 0.25 molar solution of hydrochloric acid. So since we always use liters when it comes to molarity, I'm going to change that to liters. So 0.0500 liters for the HCl. It's also 0.25 molar. So 0.25, I prefer to write it as moles per liter. You can write it as molar if you'd like. It's totally up to you. So with any Stoich problem, if you remember, you're always given information about one substance and you're trying to find something else for another substance. And the way to link them is always through moles. So the first step when you do Stoich is find the moles of the substance that you have information about. So in this case, it would be HCl. Second step, find the moles of the substance you're interested in. So in this case, it would be zinc. And then the third step is actually answer the question. In this case, it would be grams of zinc. So First, we want to find moles of HCl. So there's two ways that you could do that. I'll show you both ways, and you pick whichever one you would like to do in your notes. So I have 0.0500 liters of HCl. I'm trying to find moles. That's a 5 there. So on the bottom, I'm going to put liters of HCl. On top, I'm going to put moles of HCl. And the way that I link between moles and liters of a solution is using the molarity. And so my molarity here is 0.25 moles per liter, so that means 0.25 moles for every 1 liter. So then I go here, I put 0.25 moles for every 1 liter. Okay? If you choose, you can do it a different way. You could say the molarity equation is molarity is equal to moles per liter. So then my molarity is 0.25 molar. So that's equal to X moles of HCl divided by 0.0500 liters. So the answer to that is 0.0125 moles of HCl. You only need 2 sig figs, but I usually round at the end. Okay, so first step, find moles of the substance that you have information about, which is the HCl. We got it. Next, we're going to find moles of the substance we're interested in, which is the zinc. So if you're doing it this way, you can just continue on. You don't have to solve this. Right now, your liters of HCl cancel. You're at moles of HCl, so you put moles of HCl on the bottom, moles of zinc on top, and use the molar ratio. And so according to the equation, 1 mole of zinc for every 2 moles of HCl. And so your moles of HCl cancel, you end up with moles of zinc. If you chose to do it this way, that would be your first step, finding moles of HCl. Your second step would be going for moles of HCl, so 0.0125 moles of HCl. So basically the same step that we did above. Moles of HCl on the bottom, moles of zinc on top, and so 1 to 2. And so that gives you 0.00625 moles of zinc. Okay. Last step is to actually answer your question. So if you're doing it here, again, you don't have to stop in the middle. You can just keep going. So moles of zinc on the bottom, grams of zinc on top. And the molar mass of zinc is 65.4 grams. Same thing here, so you're going to go from 0.00625 moles of zinc, moles on the bottom, grams on top. 1 mole is 65.4 grams. If you calculate that, you end up with 0.41 grams of zinc, and you get that either way that you do it. 0.41 grams of zinc. The advantage to the method that I have in red here is that you don't have to stop in the middle. You just do it all in one step. You use your units to kind of guide you. So it saves you a little bit of time. The advantage to the method that's in blue here is that it makes a little bit of sense. In this case, you're going to have to stop here after step 1 to calculate the moles of HCl before you move on. You could have combined steps 2 and 3 if you wanted to, though. All right, let's try another problem. Okay, so in this problem, it asks what volume of 10th molar sulfuric acid solution is needed to neutralize 25 milliliters of 0.35 molar KOH. So this is an actual titration example. You could do this with your burette and your flask, and you add indicator, and then when it turns colors, then that's what you would when you would stop. So again, since this is talking about a chemical reaction, first step is to write your equation. So we have sulfuric acid H2SO4 reacting with KOH. This is neutralization, which is a special type of double replacement. So the two outer ones go together, you form liquid water. The two middle ones go together, you form potassium sulfate, so K2SO4. That's a 2. And again, we need to balance it, so we need a 2 here and a 2 here. I'm going to go ahead and write down the numbers that I'm given. So I'm given 10th molar of sulfuric acid. Again, I'm going to write it as moles per liter. If you want to write it as molar, that's fine. We are trying to find the volume, so I'm going to put question mark liters. For the KOH, I'm given that it's 0.350 molar, so I'm going to put 0.350 moles per liter. And I'm given the volume. I'm going to go ahead and change it to liters. So 25 milliliters would be 0.0250 liters. So, just like every Stoic problem, find the moles of the substance that you have information about, so in this case, KOH. Then find the moles of the substance you're interested in, which is the H2SO4, then answer your question. So, let's go ahead and do that. So first, moles of KOH. So I have 0.0250 liters of KOH. So I'm trying to get rid of liters of KOH, so I'll put it on the bottom. I'm trying to find moles of KOH, so I'll put it on top. And to link between moles and liters of a solution, you use your molarity. So according to this, I have 0.350 moles for every 1 liter. So I'll put that in. So 0.350 moles for every 1 liter. Again, if you don't like it that way, you can just write molarity equals moles per liter. You're given the molarity, you're given the liters, you can find your moles. Next up, find the moles of the sulfuric acid, because that's the substance you're interested in. So I'm just going to continue. So moles of KOH on the bottom, so they cancel. Moles of sulfuric acid on top. And it's a 1:2 ratio. So that gets me moles of sulfuric acid. Last step is actually answer the question. We're trying to find liters. So right now, these cancel, I'm at moles of sulfuric acid. So then I'm going to put moles of H2SO4 on the bottom, because I want to get rid of them. I want to put liters of H2SO4 on top. That's what I'm trying to find. And to link between moles and liters of a solution, you would use the molarity. So according to this, there's 0.100 moles for every 1 liter. So then you go in, you write 0.00100 moles for every 1 liter. Watch out that this number goes with the moles and then 1 goes with the liters. Now again, if you don't like this, you can always use your molarity equation. So once you are done with this step right here, at the end of this step you're going to have moles of H2SO4. So then you can write molarity is moles per liter. You would have the moles of the H2SO4. You have the molarity, which is right here, and you solve for liters. All right, last problem of the notes. This is one of my favorite problems here, and this is actually your lab calculation, so you might want to star this or circle it or something. This is pretty important here. Let's give it a star. So we have an iron ore. An ore usually means that it's a mixture of things. It has usually metal oxides and other things in it, and other impurities as well. So we have this iron ore that has a mixture of iron 2 and iron 3 ions, and because it's an ore, it has other things as well. So it's not just Fe2 plus and Fe3 plus, and obviously those ions would be bonded to something else as well. So we're given this ore. It says such an ore can be analyzed by dissolving it in an acidic solution, and then, that should say then, not them, titrating it with potassium permanganate. The permanganate ion is basically what reacts from the K plus is just a spectator ion here. So the permanganate ion is reduced to Mn2 plus, and the Fe2 plus is oxidized to Fe3 plus. So basically the MnO4 minus reacts with the Fe2 plus, turns it into Fe3 plus. A sample of ore weighing 0.3500 grams was dissolved in an acidic solution, and all the iron was reduced to Fe2+. So you would have no more Fe3+. Then the solution was titrated with, you're given the molarity of the potassium permanganate solution. It gives you the volume of the potassium permanganate solution, and it says that's the volume that's needed to reach the end point. We want to determine the mass percent of iron in the ore. So this is quite a long problem, or it's very, very wordy, and it could get confusing. So let's try to think about what we're doing here. So we have an ore. So there's your ore. This ore has a bunch of stuff. It has Fe2+ in it, it has Fe3+, and it has other stuff in it. We know that it has a total of 0.350 grams total. That's our ore with all the impurities and everything. And we're looking for percent Fe in it. Okay, so percent Fe, if I want percent of anything, that's going to be mass of that substance, so in this case, mass of the iron, divided by the total mass, and then times 100%. Okay, so I don't know what the mass of the iron is, but I know what the total mass is. It's given to me. It's the 0.3500 grams. So I'm halfway done with this problem, right? I already have the total mass here, so all I need to find is just the mass of the iron. Pretty simple, right? Okay, so then it talks about this reaction between the permanganate ion and the Fe2+. And it's saying that, so you put this whole ore into an acidic solution, and you add potassium permanganate. Basically, the acidic solution is there to kind of dissolve your ore. Then you add the permanganate solution, and the permanganate says that it turns the Fe2+ to Fe3+. So let's try to write the chemical equation for that. Okay. All right. So I have the permanganate ion, MnO4-. That's an O there. It tells me it's reduced to Mn2+. And then I also have the Fe2+ oxidized to Fe3+. So it's a redox reaction that's happening. So let's balance redox. That's a lot of fun. So let's try the iron one first. Is kind of easier to balance. So you balance the atoms that are not oxygen or hydrogen first. So one iron, that's good. Next, oxygens and hydrogens that are none there. Next, your charge. This is +2, +3, so we're going to add an electron on that side, and that's balanced. The other reaction, the other half reaction, 1 manganese, 1 manganese, that's good. Oxygens, 4 and none, so we're going to add 4 waters. Next are hydrogens, none on the reactant side, 8 on the product side, so we're going to add 8 H pluses here. Next are the electrons, and so here your total charge is +7, here your total charge is +2. Remember, you add your electrons always to the more positive side. We need 5 electrons on that side. Next, you want your electrons to equalize, so we have 5 and 1, so we're going to multiply this by 5. So we get 5 Fe2+, yields 5 Fe3+ plus 5 electrons. Next, you're going to add your two reactions together. So we have, let's see, 5 electrons plus 8 H plus MnO4- plus 5 Fe2 plus yields Mn2 plus 4 H2O plus 5 Fe3 plus 5 electrons. If you did it correctly, your electrons should always cancel, and they do. Nothing else cancels. Next step says if basic, you neutralize your H pluses with hydroxides. In this case, they keep telling us that it's in an acidic solution, so that means we don't have to do that step, and so we're basically done. We just need to check it. So let me rewrite it a little bit neater. So 8H plus MnO4 minus plus 5 Fe2 plus yields Mn2 plus 4 H2O plus 5 Fe3 plus. Let's check that it's balanced. So hydrogens, we have 8. 4 times 2 is 8. Manganese 1 and 1. Oxygens 4, 4. Irons 5 and 5. The charge, this is plus 7, minus 1, and plus 10. So the total, this is plus 8, minus 1, and plus 10, so the total is plus 17 on that side. On this side we have plus 2, this is 0, this is plus 15, so plus 2 and plus 15 is plus 17, so it is balanced. So this is our balanced chemical reaction here. Now the reason why we had to write this is because any stoic calculation needs molar ratios, and so we needed to balance it here. And also it's fun. So anyway, the whole point of this was because we wanted to figure out the percent iron in our ore. And so we need the mass of the iron, so we can divide by the total mass of the ore. And so we are trying to find the mass of the iron in here. So this is what we're looking for, is the grams of iron. Now, if you want to put your question mark iron here, that is fine as well. The mass of this iron is the same as the mass of this iron. It doesn't really matter, you know, whether it has an extra electron or not. Electrons, you know, their mass is negligible. So either you put your question mark here or your question mark here. It really does not matter. You can pick whichever you want. Let's see what other information we have. If we look at the problem, we're given stuff about the permanganate, information about the permanganate. We're given the, we're given the molarity right here, and we're also given the volume. So let's write those down underneath here. So the molarity is 1.621 times 10 to the negative second. I'm going to write moles per liter. And my volume is 0.04156 liters. I just converted that to liters from milliliters. All right, so this is just a regular stoic problem at this point. We're looking for the mass of our iron, but we're given information about our permanganate. So as always, you're going to find the moles of the substance you have information about. So in this case, the MnO4 minus. So again, you do it whichever way you prefer. I'm going to use the way where I cancel out my units. So that's my volume of the MnO4 minus. So on the bottom, I'm going to put liters of MnO4 minus, so it cancels. On top, moles of MnO4 minus. To link between moles and liters of a solution, you use its molarity. Its molarity is this many moles for every 1 liter. So that's what I'll write here. So 1.621 times 10 to the second moles for every 1 liter. As always, you can use the molarity equation. You are given the molarity, you're given the liters, solve for the moles, if you prefer that way. Okay, I'm at moles of permanganate, so I have the moles of what I have information about. Next, I find the moles of what I need, and I use the molar ratio for that. So on the bottom, moles of MnO4 minus. On the bottom, moles of Fe2 plus, and again, you can use the 3 plus, it doesn't really matter. Either way, it's a 5 to 1. So those cancel, I end up with moles of Fe2 plus. Next, I answer the question. And so the question was, I was trying to find the grams of the iron so I can plug it in to find the percent iron. So on the bottom here, I'm going to put moles of Fe2 plus and then grams of Fe2 plus, and I use the molar mass. Now on the periodic table it doesn't give us the molar mass of Fe2 plus, but it gives us the the molar mass of Fe. Molar masses of Fe or Fe2 plus or Fe3 plus, again, are all the same because the electron's mass is negligible almost. So it doesn't matter if it lost a couple of electrons, it's not going to change its mass by much. So 55.8 grams. Moles cancel. Go ahead and calculate that. I'll give you a minute. All right, so you end up with 0.188 grams of Fe2 plus. That's not our final answer. Remember, we were trying to find percent iron in our ore. And so he said percent iron is the mass of iron over the total mass times 100%. So we have the total from before. We just calculated mass of iron. Now we're going to plug it in. So let's do that down here. So percent Fe is equal to mass of Fe over total mass times 100%. So we got 0.188 grams of Fe2 plus divided by 0.3500 grams total times 100%. We'll go ahead and calculate that. So I got 53.7%, and that is our answer. Good question. I guess I should have pointed that out. Why is it that the mass of the total iron is just the mass of the Fe2 plus when I know that my ore had both Fe2 plus and Fe3 plus? So the reason why I can do that is because it says that the sample of ore was dissolved in an acidic solution and all the iron, so all the iron here was reduced to Fe2 plus. So all of my ore turned into Fe2 plus, all the iron in my ore. So there was no more Fe3 plus. And then I took that Fe2 plus, all that it turned into, and reacted it with my permanganate here, and I turned all of my Fe2 plus into Fe3 plus. So whether you had solved for this or this by itself, that would have given you the mass of the total iron in your sample. All right, hope that helped. You guys have a wonderful day.